You ever see a graph in an article or a presentation and think, wow, that's a huge effect? Well, what if I told you that the very same data could be presented to make that effect look, well, completely insignificant? Today, we're going to pull back the curtain on how scientific graphs can be designed to mislead you. And more importantly, we're going to give you the tools to spot the trick every single time.
So here's how we're going to break it down. First, we'll get into a core science concept I like to call the "it depends" effect. Then we'll uncover a huge problem hiding in the data. We'll see the visual illusion it creates. I'll give you 3 simple rules for finding the truth. And finally, we'll talk about why all this really matters to you.
All right, let's dive right in. See, to understand how a graph can lie, you first have to understand the kind of truth it's trying to show. And in the world of science, the truth is almost never a simple yes or no. The real answer is almost always, it depends.
So let's take a real question from a study. Does having more confidence in your own abilities, what researchers call self-efficacy, make you go out and ask for more feedback at your job? You'd think that's a pretty straightforward question, right? It's either yes or no.
But of course, the answer is a little more complicated than that. It depends on something else entirely. And this idea, that the link between two things is almost always being nudged by a third thing, that's pretty much the foundation of modern science.
And that "it depends" relationship? Well, scientists have a formal name for it, an interaction effect. Think of it like this. Sunshine helps a plant grow, right? But the effect of that sunshine depends on whether the plant has water. Without water, all the sun in the world won't do a thing. That's an interaction effect, and it's absolutely central to our story today.
Now, these interaction effects are, they're crucial. They help us understand the nuances of the world, but here's the kicker. 2 researchers, Kevin Murphy and Herman Agunas, discovered that these critical "it depends" moments are being systematically reported in ways that are just seriously misleading.
And they didn't just look at any old studies. They went straight to the top. They reviewed every single 2020 article that tested one of these interactions in 4 of the most prestigious, top-tier management journals on the planet. And what they uncovered wasn't just a few mistakes here and there. It was a deep, systemic problem.
In total, they dug into 96 different papers from some of the top researchers in the field. Now get this. Of the papers that actually used graphs to show their results, nearly 68% of them presented an incomplete picture, a picture that could make a really weak effect look incredibly strong. On top of that, almost 70% didn't even give readers a clear number, an effect size. That tells you just how strong the relationship really is. So they were giving you all the wow from the visual, but none of the how much.
So what's the bottom line here? A tiny, tiny fraction, just over 5% of studies, did both things right. They gave you an honest graph and a clear number to back it up. That means for nearly 95% of these studies, readers were simply not getting the whole truth. Okay, so how does this actually work? How can a graph, which is supposed to be objective data, lie to your face? Well, it turns out it's a surprisingly simple little trick. It's all about framing. All right, take a look at this. This graph shows that feedback-seeking data we were talking about earlier. You see those lines? They're steep. They're pulling apart. The visual message is crystal clear. This is a powerful, important effect. Anyone looking at this would think, wow, that's a big deal. But is it? Is it really a big deal? This is the one question that the researchers found was almost never getting a straight answer. When you zoom out and look at the grand scheme of things, how much does this effect really matter? So here's the trick. It's a classic move called truncating the y-axis. See, the original data was measured on a 7-point scale. But the graph on the left, it doesn't show you the full scale. It zooms way in on just a tiny 2-point slice of it. And in that tiny, magnified window, even the smallest changes look absolutely massive. It's kind of like looking at a tiny crack in the sidewalk with a microscope and thinking the whole city is about to crumble. And now, here's the truth. This is the exact same data. The numbers haven't changed at all. The only thing we've done is zoom out to show the full, honest 1:7 scale. And just like that, poof, those dramatic, steep lines are now nearly flat. That powerful effect is suddenly revealed for what it is. Pretty weak. Nothing changed but the frame. So, we've seen the problem. We've seen the trick. The big question now is, what can we do about it? Well, the great thing is, the researchers gave us a super clear toolkit, 3 simple rules to protect yourself from being fooled.
You can think of this as your personal data defense system. Number 1, demand the full picture. Number 2, find the effect size. And number 3, understand the meaning. Let's quickly break each one down.
Okay, rule number 1 is your first and best line of defense.
From now on, whenever you look at a graph, the first thing your eyes should go to is the vertical y-axis. Does it show the full possible range of the data, or does it start at some weird number in the middle? If it's not showing you the whole picture, there's a good chance it's trying to exaggerate something.
Rule 2. Look past the pretty picture and find the hard number. A good, honest study will report something called an effect size. You might see a symbol like delta, r squared. This little statistic cuts through all the visual noise and tells you, objectively, just how strong that "it depends" effect really is.
And finally, Rule 3 is about asking, so what? Who does this effect actually matter for in the real world? As the researchers point out, a lot of these interactions are only really significant for tiny groups of people at the extreme ends. Remember our example? The effect only mattered for people with very low confidence. For pretty much everyone else, it meant nothing. So always ask, is this a universal truth, or is it just a niche finding?
And look, this isn't just some nerdy academic debate. The implications here are absolutely huge. We use scientific research to make major decisions, in business, in public policy, even in our own personal lives. And if the research we're relying on makes weak findings look strong, we're going to end up chasing ghosts and making bad choices, all based on a simple visual illusion.
I mean, the researcher's own conclusion says it all, and it's pretty powerful. They say, there appears to be bias in the way these effects are displayed, which could lead to the impression that weak interactions are strong ones. This isn't just about a few sloppy charts. This goes to the very heart of scientific integrity.
So the takeaway here is simple. Become a critical consumer of data. Armed with these 3 rules, you now have the power to see past the visual tricks. So the next time you see a graph that's making some big dramatic claim, just pause. Ask the tough questions. Ask yourself, am I looking at the whole truth, or am I just falling for a trick of the scale?